Imagine a star, much more massive than our sun, nearing the end of its life. It has exhausted its nuclear fuel and gravity takes over. The star implodes, collapsing in on itself. This catastrophic event, a supernova, is one of the most energetic explosions in the universe. In the aftermath, a neutron star emerges. Neutron stars are incredibly dense, packing more mass than the sun into a sphere only about 20 kilometers across. The birth of a neutron star marks a new chapter in stellar evolution. The formation of a neutron star is a dramatic event, a testament to the immense forces at play in the universe. It all begins with a star much more massive than our sun, at least 8 times more massive. These stars burn through their nuclear fuel at a faster rate than their smaller counterparts. As the star runs out of fuel, the outward pressure from nuclear fusion weakens. Eventually, gravity overpowers this outward pressure, and the star's core collapses in on itself. This collapse happens with incredible speed, reaching velocities of up to 70,000 kilometers per second. The core collapses so rapidly and violently that it bounces back outwards, creating a shock wave that rips through the star's outer layers. This shock wave, carrying with it an immense amount of energy, is what we observe as a supernova. In the heart of this explosion, the core of the star continues to collapse. The protons and electrons in the core are forced together by the immense pressure, merging to form neutrons. This process gives the neutron star its name and its incredible density. Neutron stars are among the densest objects in the known universe. Imagine taking a teaspoon of neutron star material. It would weigh approximately 6 billion tons. That's equivalent to the weight of Mount Everest, compressed into the size of a sugar cube. This extreme density is a result of the way matter is packed within a neutron star. In a normal star, atoms are spaced relatively far apart. But in a neutron star, the intense gravitational pressure forces the atoms together, squeezing them down to their smallest possible size. Protons and electrons are crushed together, forming neutrons. These neutrons are then packed together as tightly as possible, creating an object of unimaginable density. To understand this density, consider the fact that the atoms that make up all matter, including ourselves, are mostly empty space. If you were to remove all the empty space within atoms, you could fit the entire human race into the volume of a sugar cube. Neutron stars are essentially this concept taken to the extreme, with all the empty space squeezed out of atoms, leaving behind an object of almost incomprehensible density. Despite their incredible density, neutron stars are surprisingly small. A typical neutron star has a diameter of only about 20 kilometers, which is roughly the size of a city. This makes them incredibly difficult to detect, as they emit very little light compared to stars like our sun. However, what they lack in size, they more than make up for in mass. A neutron star can have up to twice the mass of our sun, all packed into this tiny volume. This means that the gravitational pull at the surface of a neutron star is immense, about 200 billion times stronger than the gravity on Earth. The combination of extreme density, small size, and immense gravity gives neutron stars some very strange properties. For example, time itself is affected by the gravity of a neutron star, running slower on its surface than it does further away. This is a consequence of Einstein's theory of general relativity, which predicts that gravity can warp the fabric of space-time. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space like lighthouse beams. These beams are caused by the rapid rotation of the neutron star and its incredibly strong magnetic field, which can be trillions of times stronger than Earth's magnetic field. As the pulsar rotates, its magnetic field lines channel charged particles, accelerating them to incredibly high energies. These charged particles then emit radiation along the magnetic field lines, creating the beams that we observe. When these beams sweep past Earth, we detect a pulse of radiation, hence the name pulsar. The discovery of pulsars in the 1960s was a major breakthrough in astronomy. It provided the first concrete evidence for the existence of neutron stars, which had previously been theoretical objects. Today, pulsars are used as cosmic clocks, their precise pulses helping astronomers study a wide range of phenomena, from the properties of matter under extreme conditions to the structure of our galaxy. Neutron stars, despite their extreme properties, are incredibly faint objects, making them difficult to detect. Their small size and relatively low luminosity mean that they are often outshone by other celestial objects. However, astronomers have developed ingenious methods to observe and study these cosmic enigmas. Radio telescopes designed to detect radio waves have been instrumental in discovering and studying pulsars. The beams of radiation emitted by pulsars are particularly strong in radio wavelengths, making them detectable even from vast distances. These telescopes can detect the faint pulses of radiation emitted by pulsars, allowing astronomers to measure their rotation periods, magnetic field strengths, and other properties. X-ray telescopes, such as the Chandra X-ray Observatory, have also played a crucial role in observing neutron stars. These telescopes can detect the high-energy X-rays emitted by the hot surfaces of neutron stars and the intense magnetic fields surrounding them. By studying these X-ray emissions, astronomers can learn about the internal structure and composition of neutron stars. Neutron stars, despite their seemingly esoteric nature, hold the key to understanding some of the most fundamental questions about the universe. They are natural laboratories for studying the behavior of matter under extreme conditions that cannot be replicated in any laboratory on Earth. The study of neutron stars provides insights into the nature of gravity, the properties of matter at incredibly high densities, and the processes that occur during supernova explosions. The extreme gravitational fields around neutron stars provide a testing ground for Einstein's theory of general relativity. By studying how light is bent by the gravity of a neutron star, astronomers can test the predictions of general relativity with unprecedented precision. Furthermore, neutron stars are thought to play a crucial role in the creation of heavy elements in the universe. The intense heat and pressure generated during supernova explosions, the events that give birth to neutron stars, are thought to be responsible for the synthesis of elements heavier than iron. These elements, including gold, platinum, and uranium, are scattered throughout the universe by supernova explosions, eventually becoming incorporated into new stars, planets, and even life itself.